Hi guys, welcome to your 1.3 notes. Today we'll be talking about real numbers and the number line. By the end of the day, students will be able to classify, graph, and compare real numbers. In addition, you will also find and estimate square roots. So let's start off with square roots. We say that a number a is a square root of a number b if a squared equals b. For example, we say that 7 is a square root of 49 because 7 squared is 49. So 7 squared equals 49. That is, when we say 7 squared, that's 7 times 7, and that's equal to 49. Now we have this other object called not a square root. This is what I get for looking at what I'm writing. The radical symbol. Guys, it's radical. Ha. The radical symbol looks like this. It's got like this roof on top, and then it juts down and then has a little like checkmarky kind of thing. That's the radical symbol. That indicates a non-negative square root, non meaning not, a negative meaning like a negative sign. So non-negative is it's greater than or equal to 0. The expression under the radical symbol we call the radicand. It's like radical, but man, I should really slow down. Radicand, like that. And then together, these two items form a radical. So here in our example, we've got the radical symbol, which is this guy right here. And then we also have the radicand. The radicand, in this case, is 4, because it's under the radical symbol. This whole radical is equal to 2, because 2 squared is 4. So look at each of these examples and write the simplified form of the expression. That means the simplified form of this radical was 2. What is the square root of 81? It's 9. And what is the square root of 9/16? Well, that's 3/4. If you want more explanation, remember to look up the Examples Explained video when you're done. So going the opposite direction from a square root, now we're going to take a perfect square. Did I use purple up here? I did. Let's use red. A perfect square. A perfect square is when you take an integer, like any positive whole number, and you square it. For example, 3 squared is 3 times 3, which is 9. And 2 squared is 2 times 2, which is 4. 1 squared is really fun because it's just 1 times 1, which is 1. So 1 is its own square. In fact, it's handy to have a list of perfect squares. Perfect squares are 1 squared is 1, 2 squared is 4, 3 squared is 9, 5 squared, and I skipped 4 squared. 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. Awesome! And then the squares keep going on. And guys, there's literally an infinite amount of perfect squares. So we're just gonna stop where we run out of room. But it's nice to keep these guys in your head, especially if you encounter them on a later problem. Alright, cool. Let's put this into practice. So, lobster eyes are apparently made out of little tiny squares, and under a microscope, they look like graph paper. They look like this, which is cool. Fun fact, saw a lobster at the beach this weekend, so I should have gone back and really taken a better look at him. Anyway, so a scientist measures the area of one of the squares. You'll recall that area is the space inside of the object. So like this amount of space in here, is 386 square microns. We're going to go ahead and label that 386 square microns. What is the approximate side length of the square to the nearest micron? Well, remember to find the area of the square. The area is the length of the sides squared. That's where we get the term square from. So if this square has side length s for side, that means that 386 is s squared. And if we want to figure out what s is, we're going to take the square root of each side, because this square root here will cancel out the square. So what does that give us? That gives us, well, s is the square root of 386, of course. Now I know what you're thinking. You're thinking, man, Miss Van Dyke, that's not helpful. and I agree, because I look at this and I go, well, I don't know. But I'm going to give you a little frame of reference here. Remember when I said that the list of perfect squares is going to come in handy? If I had kept going, I would have told you that 361, that's 19 squared, and 400, that's 20 squared. And check it out. Watch this. 386 is between those numbers, like on the number line. If we were to have a nice throwback to elementary school, put numbers on the number line, like if this is 360, 370, 380, 390, and 400, well, we know that 400, that's 20 squared, and we know that 361 is 19 squared. Then s squared, which is 386, that's right there. So I look at this and I see, this is closer to 20 squared than it is to 19 squared. So we're going to say that s, because it's closer to 20, we're going to say that's approximately 20. And that's what they asked for. They asked for the nearest micron, and it's closer to 20 than it is to 19. So there you go, approximately 20. And 20 microns, guys, is very teensy tiny. So emphasis on that, tiny. So that's squares and square roots. Let's talk about sets. We're like halfway done. Cool. All right, so a set, while it is a tennis term, we're not going to use it in that way. We're going to say it's a well-defined collection of objects. So in English, that means it's like a group of stuff. Or it's a basket of numbers. I like that. It's a basket of numbers. Or of stuff. It's not exclusive to numbers. And we say each object is called an element of the set. So each thing in your basket is called an element. And then a subset is like a smaller basket inside your basket. It's like a little group within your group. For example, if we were to look at the people inside this class, the people in this class, subsets could be things like all the boys in this class, or people who watch anime. And then you could also say people who spell watch correctly, which would not include me, apparently. So there you go. So this is important because we're going to look at sets of numbers. We want to be able to describe numbers just like we described people in our class. We want to be able to describe numbers. And here are a bunch of sets of numbers. I'm going to talk through them real quick, and then you're going to tell me which subsets a number belongs to. Now, my niece is 4 years old, and when I ask her about numbers, if I ask her to count, she will say things like 1, 2, 3, 4, and that's something that comes naturally. our natural numbers, we also call our counting numbers. They're what you use when you count. And then our whole numbers are all of our counting numbers and also 0. That's it. I like to remember this because whole sounds like there's a hole in it, and 0 is shaped like a hole, and then you have O, which is like a hole. The integers, you just take the natural numbers and you make them negative. There's like an N for negative, and not to be confused with the N for natural. And then finally, a rational number is one that can be written like a fraction. See this fraction bar here? Ratio, in fact, means you can write it as a fraction. So our helpful hint here is that ratio means fraction. And whenever you have a decimal, we say it's a repeating decimal. So it's a fraction or repeating decimal. There's a way to write all repeating decimals as fractions, and if you're really curious, come ask me in office hours and I would love to help you. Oh, that was a weird sound. Okay, so this bar right here means that the 1, 2 repeats, so that's 0.012121 forever and ever. And then here on this 0.63, we have like a hidden 0, so this is technically 0.63. 0, 0, 0, 0, 0, 0, 0 for forever. So we say the 0 is the repeating part. So that repeats. The 1, 2 repeats. So there you go. And then finally, our irrational numbers. Are you ready for this? I don't think you're ready, but too bad. Irrational, you see that ratio in there? We've seen that before. That means it's a fraction. Okay, cool. You know, I'm just gonna take this and I'm just gonna copy it. Right? Except, guys, guess what? There's that ear in front of it, and this ear means not. So you can't do it. So it means it doesn't repeat. It's not a fraction or repeating decimals. So basically weird numbers. Yeah, they're weird numbers. I don't even know if I spelled that right. Yeah, square root of 3 doesn't repeat. Pi, which is approximately 3.1415926, blah, 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 okay? It never repeats. But you look at this guy and you go, oh, I notice a pattern. There's 2 zeros and then 3 zeros, but that's a pattern. It's not repeating. It's not the same thing over and over and over again. So there you go. So those are all the real numbers. So go ahead and name, for example 3, you're going to list all of the subsets that each number belongs to. For example, you'll notice that we have the number 0, which is an integer. 0 is also a whole number. This means that 0 is also rational because it's within that set. It's also a real number because it's inside of here. If you were to think of the real numbers as a basket, and there are 2 baskets within the real numbers. You have the rational basket and the irrational basket. But then going even further, you have a basket within a basket within a basket within a basket. If y'all have seen Inception, that's what it's playing at. A dream within a dream within a dream. Same kind of thing here. A set within a set within a set within a set. That's what a subset is. A set within a set. So if I wanted to list all the subsets that 0 is in, 0 is a whole number, it's an integer, it's a rational. It is rational, it's a rational number, not it's irrational, and it is a real number. Let's go ahead and list all of the subsets to which the real numbers belong. Pause it and check your answers. Okay, 15 is a natural number, and therefore it is whole. It's also an integer, and it's a rational number. If you want to be super pedantic, you can say, and it's also real. So there you go. Negative 1.4583 has a terminating decimal. That means it ends. where there's like the 0, 0, 0, on and on and on, that means it's rational. And because it's rational, it's real. But it's not a natural number because it's negative. It's not a whole number because it's negative. It's not an integer because it has stuff after the decimal point, but it's rational and it's real. Square root of 57, not even rational. It is irrational. And it's real. So there you go. Okay, we have one little thing left. And this is an inequality. What color haven't I used yet, guys? Brown. An inequality is a mathematical sentence that compares the values of two expressions using an inequality symbol. If we were to look at the word inequality, this is one of my favorite things to do, by the way, is to break it up into word parts. Itty just means it's a noun. That means it's a thing. That's not very important. Inside, you see this equal. Hopefully y'all recognize that equal means equal, as in same. But then you'll remember from irrational numbers that when you have the I in front, that means not. So these are numbers that are not the same, or rather these are expressions that are not the same. So you can have a symbol like this guy, which means less than, or this guy, which means greater than. Or you can have this funky hybrid, which means less than, but also equal to, or equal to, and then greater than, or equal to. I like to remember this because it's got the little equal sign right here. Right there, an equal sign and an equal sign. Cool, huh? All right. So for example number 4, let's write an inequality that compares the square root of 17 and 4 1/3. So there are two ways to do this. You can use a number line or you can use a calculator. How about we do a calculator here and then we'll use a number line down here. Good deal? Well, I didn't hear anyone say otherwise, so let's go ahead and do that. All right, so when I plug in the square root of 17 into my calculator, because we're doing this the fast way. You know what? I'm gonna back up. Let's not do this the fast way. Oh, I can hear you guys so excited. Yes. Awesome. Okay. So when I list square numbers, I know 9 is 3 squared, and I know 16 is 4 squared. Remember, these are perfect squares from earlier. And then keeping on going, I've got 25 is 5 squared. Now 17 is just bigger than 4. Then 4 squared was 16. 17 is bigger than 16, but not quite close to 25. So we know that the square root of 17 is going to be greater than 4, but is it greater than 4 1/3? I don't know. Let's plug it into the calculator real quick. Oh, you guys, it turns out to be 4.123 blah, 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 something. Whereas 4 1/3, that's 4.3333333, and so on. We've 4.3 repeating, which is what that little hat means, repeating. Now, if I were hungry and I needed to have some sandwiches, I would much rather have 4.3 sandwiches than 4.1 sandwiches because 4.3 is bigger. That said, if I had 4.1, 2, 3, etc., and 4.333, etc. on the side, and I had my big hungry shark mouth, throwback to 2nd grade, the shark mouth would be pointed towards my 4.3 sandwiches, right? You remember having like little teeth and you've got like the sharky guy and he wants to eat this because it's the bigger fish. Did you guys ever do that? Or do you just think I'm crazy? The two are not mutually exclusive. So anyway, So that tells us that the square root of 17 is in fact less than 4 1/3. That's our inequality. Okay, we're almost there. We're going to put these numbers in order from least to greatest. And now that I zoom out, I realize how crooked my number line is. Yikes. Okay, so let's get a good decimal approximation and put them on our number line. So I've got the square root of 4. I know the square root of 4 is 2. So I'm going to need to put 0, 1, and 2 on the number line. Put 4. I know negative 2/3 is approximately negative 0.66666666. Square root of 2 is going to be between 1 and 2. I know that it's actually about 1.414 because of other math things. And finally, negative 1.5. So I'm going to keep my number line going down to negative 1 and negative 2, and let's put these guys on here. All right, the square root of 4 we said is exactly 2, so square root of 4 goes right there. 0.4 is a little bit less than a half, so if my half is like there, I'm going to put 0.4 there. Oops, just kidding. 0.4 goes here. Negative 2/3 is, well, it's going to be 2/3 of the way through here, so I can estimate like thirds. Yeah, it's going to go right there. Awesome. So that was negative 2/3. The square root of 2 is, 1.4, that's almost 1.5, right? So we can put it about halfway, but just a little bit not. So there you go. And finally, negative 1.5. Put that exactly between your negative 1, negative 2, negative 1.5. Ah, we did them. We put them on the number line. And now, guys, this makes our job a whole lot easier because we can put them in order by going from least, which is way on this end over here, over to greatest, which is way on this end over here. So, in order, we have negative 1.5, negative 2/3, 0.4, square root of 2, and the square root of 4. That was perfect. Good job, phone. You're done. All right. As I check the email I just got from my aunt, go ahead and write the most important thing from this lesson, a question or something you wonder about, and then make up a question like that would show up on a quiz for this lesson. Remember to show all your work on your homework and have a wonderful day as you compare real numbers and estimate square roots.